We began the second major concept of calculus with that of the derivative, and we start by defining the derivative in terms of the previous concept, limits. By the end of this, you should be able to develop and use the limit definition of the derivative. The tangent line problem is one of the fundamental ideas of calculus, and if you have a point C, f of c, where c is the x-coordinate and f of c is its y-coordinate, we can determine the slope at that point, the slope of the tangent line, by picking another point some distance away from it, called c plus delta x and f of c plus delta x, and determining the slope of the secant line through those points. By doing that, we can then determine the slope of the tangent line. And that point c plus delta x and f of c plus delta x is some arbitrary distance delta x away on the horizontal axis. We're bringing that second point closer and closer to the first point. We eventually wind up with the tangent line. So the slope between those 2 points is given by y2 minus y1 over x2 minus x1. Here's the y and x coordinates of the second point that we chose that's delta x away, and here is the y and x coordinates of the first point. Now when we simplify this, we wind up with this very important idea, that the slope of the secant line between the 2 points is f of c plus delta x minus f of c over delta x, because in the denominator the c's cancel out. Now what we're trying to do is make delta x smaller and smaller, and if that sounds like a limit, it absolutely is. And this is the definition of that tangent line with a slope of m. The limit as delta x is brought closer and closer to 0 is f of c plus delta x minus f of c over delta x. That is the slope. That is going to be the derivative. That's the slope of the tangent line at the exact point c comma f of c. Let's look at an example. Let's find the slope of the graph of f of x equals x squared plus 1 at the point negative 1 comma 2. And then we'll find the equation of the tangent line that goes through that point. Here's what it looks like. Here's the point negative 1, 2 along the function x squared plus 1. We know the tangent line will look something like this. We want to find its exact slope and its equation. So we're going to use the limit definition of that slope. F of x is equal to x squared plus 1. And here's our limit definition of that slope. Well, what we're going to do is we're going to take f of x plus delta x, and that's this part right here. F of x plus delta x is equal to the input squared plus 1. So since the input is x plus delta x, we're going to square the x plus delta x, and then we're going to add 1, because that's what the rule of the function is. Then we're going to subtract f of x. F of x is x squared plus 1. So we're going to subtract the entire quantity x squared plus 1. So we've got f of x plus delta x here minus f of x. Be careful to distribute that negative to both terms. And it's all divided by delta x. We can distribute out the x plus delta x when we square it, and you get x squared plus 2x delta x, that's the middle term, don't forget about it, plus delta x squared, plus the 1. So all of this is an expanded out version of f of x plus delta x, minus x squared minus 1. Notice we distributed the negative, all divided by delta x. Okay, so we've simplified this, and now we can simplify it because some terms look like they're going to cancel out. You can see the x squareds cancel each other out, the 1 and the negative 1 cancel each other out. So we're left with the limit as that delta x approaches 0 of delta x, because we can factor out a delta x out of both the remaining terms, times 2x plus delta x all over delta x. Well, yes, we can cancel out the delta x in the numerator and the denominator, and we're left with 2x plus delta x. Well, as delta x approaches 0, this term drops out and becomes 0. So what's left is 2x. Therefore, the slope at any point along this function of x comma f of x is given by the slope equals 2x. Notice the slope itself is no longer just a number, it is a function that changes throughout. So what's the slope of the point negative 1 comma 2? What we're going to do is we're going to take that x coordinate of negative 1, plug it into the function, that is the function of the slope. Put in a negative 1 for x, you get the slope is negative 2 at that point. So the equation of the tangent line, this is putting it into point slope form. If we put in a -1 for x and a 2 for y, -2 for the slope, this is y minus y1 equals m times x minus x1, if you'll recall from Algebra 1. So notice a couple of things that are different from what you've done before. Since this function is not a line, its slope is constantly changing. And in fact, its slope is given by the function 2x. At the instant the point is -1, 2, the slope happens to be -2. So the limit is used to define the slope of a tangent line, and it's also used to define one of the two critical operations of calculus, which we call differentiation, taking the derivative. So the definition of the derivative of a function is exactly what we had learned just before, which is the slope of the secant line. It's the point brought closer and closer to the original point so that the secant line becomes the tangent line. The derivative, which we're going to call f prime of x, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x, that's y2 minus y1, all over delta x, which is the difference between the two x coordinates, x2 minus x1, where delta x is being brought closer and closer to 0. And this is again read f prime of x. There are other ways to show it too. dy dx, meaning the difference in y over the difference in x. Y prime is another way. The derivative of f of x dx, and less commonly capital Dx, the derivative of y with respect to x. So let's try it with the square root of x. F of x equals the square root of x, and we're going to try and find f prime of x, the derivative of this function. We're going to use the result to find the slope of the graph of the function at the points 1, 1 and 4, 2. And also we're going to answer the question, what happens at the point 0, 0. So we're going to use that limit definition of the derivative in our function, f of x equals the square root of x. So we've got the limit as delta x approaches 0 of f of x plus delta x. So what we're doing is we're taking x plus delta x, and it's the input to the function, and that's what this part is, minus f of x, which is the square root of x, all over delta x. Now that is a combination of radicals, so the way we're going to get rid of that is by multiplying it by its conjugate. And here's the conjugate of this numerator. When we do that, and we do some simplifying, we wind up with x plus delta x minus x. We multiply numerator times numerator over a more complicated, admittedly, denominator, square root of x times this term here. When we simplify, the x's are going to cancel out, and the delta x's are going to cancel out because we can take a delta x out of the numerator and the denominator, and so that becomes a 1 in the numerator. And now we're going to put a 0 in for delta x because we can do direct substitution now. You remember from limits, what we're doing, the limit is delta x approaches 0 of this. We're going to substitute in a 0 for delta x. That leaves us with 1 over 2 square roots of x. So the function for the derivative, the slope of the tangent line of the original function, is equal to 1 over 2 square roots of x. So at the point 1, 1, we put in a 1 for x. The slope becomes 1/2. At the point 4, 2, we put in a 4 for x, becomes 1 over 2 times 2, or 1/4. What happens at the point 0, 0? Well, the slope's undefined because if we put in a 0 here, we get division by 0. Now let's look at the graph, and the calculus is going to be confirmed by the graph. At 0, 0, we have a vertical undefined slope. At 1, 1, we're going to see the slope as 1/2. And at 4, 2, the slope is going to be 1/4. And notice the further along we get to the right on that graph, the smaller the slope gets. So now you've seen the limit definition of the derivative. You defined a fundamental concept of calculus derivative by using the limit definition. And you've used it to find the slope of functions.